So like Ben said, my name is Rob and Getz. I'm with Analog Devices. What we'll be talking about is just some common terms, definitions, these kinds of things. The focus of this talk is going to be everybody's favorite subjects, grammar, nouns, adjectives, and numbers. Numbers in science, numbers in mathematics. And whenever I start these kinds of talks, which are more at the introductory level, I always try to go back to see what other people have done. What we learned in high school or grade school that everybody should have remembered. So I found these great slides from the University of Mass, where this grade 5 teacher, Miss Kittredge, is going over nouns, verbs, and adjectives. And nouns are things like flowers, things like bandwidth, things like samples. Adjectives are words that describe those nouns, like the bowl is red and shiny, or the Pluto has a maximum sample rate of 1/61,440,000 Hertz. And again, these are just nouns and adjectives. But that would be a super complicated way to say things. So we say, megasamples per second, and then because we're electrical engineers, we try and put it in a nice acronym so nobody can understand it except other electrical engineers. On the number side, numbers in science versus mathematics. Numbers in science, this is actually a presentation that was, funded by the Haystack at MIT, where they actually do a lot of outreach at the high school science level, where they have numbers in science have units. Numbers in mathematics don't have units. Numbers in science always have some associated uncertainty or ambiguity. There's always significant digits. And numbers in mathematics, every number in your calculator, every number in GNU Radio, every number in MATLAB, that's significant to n numbers of digits. And the other kind of issue is, units in science are typically driven from a measurement, where numbers in mathematics are driven from concepts or ideas. Making measurements, there's always uncertainty. Nothing is exact. And we'll talk about that in a little bit as well. Reporting a measurement, usually when engineers and scientists report measurements, they always say what the uncertainty is. It's 199 millimeters plus or minus 1 millimeter or milliliter, or millimeter, or how many volts things are, what the ambiguity is. And significant figures are a big issue. So in the world of software-defined radio, we have lots of mathematicians, lots of scientists, and lots of people who are bad at grammar. And so there are a lot of people who think of we have our software engineering, our hardware, SoC, DSP, FPGA folks, and communication theory is mostly mathematics. It's everything is a float, infinite precision, everything is exact, and there's no units on anything. What are the units of entropy? Digital hardware, everything is a fixed int. There can be weird numbers or weird formats, fixed point fractionals. You can have concepts in your digital logic which are 4.5 bits. And everything is exact because there's no error in your clock. When you get a clock, that's one clock cycle. On RF hardware guys, we're the best because we just make up our units. Because a dB is relative to what? And nobody really knows, and dBms are relative to something exactly, but a dB is relative to something else, and nobody knows why. And the other issue when it comes to clocks and things is we don't actually want to say how bad the hardware is, so we just leave that out. And software everything is a buffer or a vector. And each discipline feels their work is obvious, and therefore leaves out the units. So this is a big challenge when we all try to communicate of what actually we're talking about. And when you're talking from your software colleagues or your comps theory colleagues or your FPGA implementation colleagues, this can be a big problem. So we'll just kind of review some of these things, from RF to antenna. Most of the things people talk about is either bandwidth or tuning range. So bandwidth is the difference between the upper and lower frequencies, and then the tuning range. So some people will define antennas as having bandwidth. I kind of prefer to think of them having tuning range, A lot of people think that's interchangeable. But you know, especially when antennas like this one has multiple bands in it, or multiple tuning ranges that it's been optimized for. So this is a LTE antenna, and it's optimized for 824 to 894 and from 1710 to 2170. It's hard to say what the bandwidth of this antenna is as one number, but it's easy to say what the tuning range is. And then before we talk a little bit about some more things on the RF side, pre-distortion. So this, everybody should be familiar with this as a typical amplifier characteristics between power input and power output in dBm. So this is relative to a milliwatt. And as, let me see if I can make the pointer come on here. As the power increases on the input side, eventually we saturate, and this knee here is called the 1 pdB point. If we can pre-distort our signal, kind of like have this compensation, push it up the other way, then the overall signal gets to be higher power and stays in this linear region, which is what everybody wants. And from a digital comms perspective, if we have our nominal waveform and we push it through this curve without pre-distortion, we'll get a symbols that look like this. If we pre-distort things before and push it through that same power amplifier, then our output actually becomes ideal. And that's what the concept of digital pre-distortion is at a very high level. So there's kind of two approaches. The most commonly used back approach has feedback. And when we use feedback, we need this 5 times the signal bandwidth. Because what we're really trying to do is suppress these third harmonics that are outside our signal of interest. So here we have a signal. We have our channel bandwidth. And so typically this is the bandwidth plus the guard band. If you want to know what the actual channel is, we talk about occupied bandwidth. So the difference between occupied bandwidth and channel bandwidth is the guard band. So separating out your adjacent channels. And then if you are doing DPD, if we have our air interface here, so this is the LTE standards, and when they talk about channel bandwidths, everybody talks about LTE 10, but the occupied bandwidth is only 9 megahertz. Because it's a lot easier to talk about LTE 15 than LTE 13.5. And then if we're doing digital pre-distortion, we talk about synthesized bandwidth. This is the bandwidth that our observer path, that feedback path, and our DACs actually need to be able to handle, even though the signal that we're sending out is still in our occupied bandwidth. So when we're talking to each other and communicating these ideas and concepts, we need to make sure that we're using the right words for some of these topics. And including like ACLR, which is adjacent channel, like how much of my energy is being in this adjacent channel, and here is without DPD and with DPD, or the digital pre-distortion. And again, see here, 45 dB, that makes sense because it's a difference between here, and this is measured in between the peak and the peak in the adjacent channel, which is a difference in dBm, which is measured in dB. So this has been mainly for digital communication kinds of channels. For analog signals like double sideband, signal sideband, we have the same kind of thing. We have our channel bandwidth. For double sideband, we actually split things into an upper sideband and lower sideband because we're transmitting both on the same, which is why it's so inefficient. And then single sideband, we usually just talk about the bandwidth of half of it because the other half disappears. Now, in terms of the antenna, even or the receiver piece, we can have different kinds of noise. We can have total noise, receiver noise, ADC noise, LNA noise, and all of these things. When somebody says my system is noisy, the answer is like, well, why? What is noisy in your system? It's not just, we can't make these general characterizations. When we talk about receiver specs, you know, here we have the folding from ADCs. So this is typically the bandwidth that we'll talk about is half of the sampling frequency. This is from Nyquist. So we were talking the other night where, you know, Nyquist figured out his sampling theory when he was 35 years old. And I'm way past 35, and I have not done that yet. But Nyquist didn't have to worry about Xbox or Netflix. So everybody's got that on their side. But we need to make sure that when we're doing these things, when we think of like Nyquist and sample rates, we kind of understand what's going on inside the radio as well. So if we think 30 megasamples a second coming out of the radio, well, does that mean the ADC is running at 30 megasamples a second? If it was, anything that was coming in at 15 megasamples a second would alias back into our ADC, or in our adjacent channels. And that's what Nyquist says. This is the way it would work. But what ends up happening is these filters right here are only third-order Butterworths inside the chips that are used in all these SDRs. So the droop that you get is not significant enough to get rid of those aliases. So if your ADC was running at 30 megasamples, then you would see lots of signals show up from your zone 2 folding back. Luckily, that's not the way things work. What ends up happening is when we talk about an output data rate of 30 megasamples a second, the ADC is running at 245 because of these interpolation or decimation filters that are inside the radio or inside the FPGA, which allows the ADC to run at much, much higher, which gives us a first Nyquist band of 122. And even at 3 dB per decade, that analog filter is down at minus 80. And it'll continue to run down past there, so that as your things fold back, depending on a sensitive radio, you would probably see them. So we have our signal running here at 30 at 245. We set our analog filters to 19, which is the other. So we have a 30 megasample channel data rate, or a 30 megahertz channel bandwidth here. This is what we're capturing. We set these filters to be half of the bandwidth times 1.25 so that we don't actually get that much droop in the passband. And we set them to 19 because the people who write this portion of the documentation think of this is a 19 megahertz filter and this is a 19 megahertz filter, but in aggregate, it's a 30 megahertz filter from an RF bandwidth versus a baseband bandwidth. So depending upon who's writing the data sheet, if it's the baseband guy, he'll talk about baseband bandwidth. If it's the RF guy, he'll talk about RF bandwidth. So when you look at data sheets and documentations, you'll see things like 56 megahertz. But when you program these filters, the most they go to is 28. Because one is RF bandwidth and one is baseband bandwidth. It's half. But this is still has some issues because even at minus 80 dB or minus 80 dB of suppression, you will still see these aliases coming back. Which is why you need to make sure we have, we can get the same thing. We can get 30 megasamples a second here. But by adding more decimation stages or more interpolation stages, now we can actually make the DAC or the ADCs in the DAC run at 491 megasamples a second. And we can see that this is much flatter. And we also see that these knees here that were part of the noise shaping from the sigma delta have actually gone away. We've actually pushed that out because we're running the ADCs much faster. And so we still have our 30 megahertz of information coming back. But we filter that to 20 megahertz because that's all we're really interested in. And then when it comes to the aliasing, now our aliases happen at 245. That's half the sample rate. And they're at a minus 140 dB of suppression. So you won't see anything aliasing back. So making sure these radios are actually set up properly is super important to your system. And you're ensuring that your signals are going to be the best they can be. So a basic Dpd system will complicate this more, where we have LTE 4.5 or LTE 5 signal. So it's 4.5 megahertz of occupied bandwidth, where the sample rate is 7.68. It has an interpolation filter of 5x, so that it actually goes up to 25 megahertz. And that 25 megahertz is the synthesized bandwidth here. And then the algorithm inside actually runs at this 25 megahertz or at 38 megasamples a second, even though we're really only transmitting 4.5 megahertz. So depending upon what you're talking about what you're trying to accomplish, your data rates and bandwidth numbers can be much, much different. And here's actually just the numbers for the LTE. So we have, LTE 10 has a channel, an occupied bandwidth of 9 megahertz, but a sample rate of 15.36 megasamples per second. And this is for oversampling, which we'll talk about in a second. And then, that gets us to the interface between the transceiver device and the FPGA. So this typically runs at 2 or 4x the sample rate, depending upon what chip it is. This is pretty chip specific. So some of them are DDR, meaning that for every clock edge or for every rising and falling edge, you get 2 data transfers. And this is typically, the clocks are in megahertz, but it's a megabits per second transfer. And this would be for CMOS or LVDS. For things like GESD 204, which a couple people later will be talking about this week, they actually have a high-speed serialized interface. So the data comes from the ADC, gets translated into a high-speed SerDes, and then goes into the FPGA and gets deserialized. So it actually has this entire stack, which includes like an 8B, 10B encoder. And then here's actually a chart from a data sheet that says, okay, for an 80 megahertz bandwidth signal, you have 122.88 megasamples per second, and you have a GESD line rate of 491.52 megabits per second. Or sorry, 4,915 megabits per second. So the ratio between your sample rate and your line rate is times 40. And where that comes from is each sample here is 16 bits. You have IQ, so that's 32 bits. You have an 8B, 10B encoder, which is times 40, so you have 40 bits to transfer over. So it's just sample rate times 40, and that's your lane rate. And so some of these are going quite fast, like these are going over 9 gigabits per second or 12 gigabits per second to just transfer the data from the transceiver chip to the FPGA. And then there's the transport piece, like USB 2 or USB 3 or PCIe or Ethernet that goes to your host. And the transport, like for example on Pluto, is USB 2. But one of the things on Pluto is we have internal memory. A lot of devices will have internal memory for buffering. So we have like 128 meg of memory. So depending upon the sample rate, that's anywhere between a half a second and 61 seconds of memory you can store in the Pluto itself without actually having to stream any information over to the PC. So if you think of the Pluto, it takes about 4 seconds to transfer 128 meg across USB. And USB is half duplex, so a full duplex is about half of that. So we get about 32 megabytes per second, which lets us stream at about 7 megasamples a second, one way. So either transmit or receive. A USB 3 is full duplex. But you can still store half a second of information at 61.44 and then slowly stream that out the device after you've captured it. And a lot of people will do that to capture a signal and then analyze it later for like the signals intelligence or for just algorithm development. For USB 3 or PCIe, there's other platforms which is, so this has it can have up to 8 RF channels that will sample at 245 megasamples a second. So you think that's from an IQ data rate, that's 491.52 megabytes per second and 983 megabytes per second for each IQ channel. So times 8, and you can fill 4 gig in half a second. And so a lot of these things are, lots and lots of channels, lots and lots of bandwidth, lots and lots of sample rate. It makes the communications problem or the transport problem harder and harder. In terms of accurate significant digits, so this is just the PLL inside these chips. We have a reference clock, and then we have this fractional PLL. So the fractional PLL basically has a fractional part divided by some typically prime number, and then an integer part times that. So if our reference clock is 40 megahertz, to see what the smallest RF step we can do, is we just take 40 megahertz divided by 1 over this modulus number right here, and we get 4.7746 something 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 hertz. And that's the step increments that we can do, which is great when you have a 40 megahertz oscillator, exactly 40 megahertz oscillator, because then you can get 2.4 gig. You end up with an integer of 60 and a fractional part of 0, and then you get a PLL of exactly 2.40000000000 megahertz. If you find you have a clock with a 39.9998898 megahertz reference clock, because your reference clocks are not going to be 100% accurate, they may have a few ppm offset, you'll never actually be able to get to 2.4, because you need to have this piece in here needs to be 1,283.45, which you can never get to. So fractional PLLs are not floating point PLLs. They're still integer pieces that will have step sizes. And that's why you'll see a lot of radios, when you want to program them to something, won't actually be able to hit those numbers. So depending upon what you're trying to do and what your reference clock is, your carrier offset and your more advanced DSP algorithm should be able to take care of a 4 hertz offset. And that's what kind of everybody expects. Now when it comes to sample rate, it's a little bit more complicated, because we have baseband clocks which have the same kind of thing. So our baseband clock can kind of go in 19 megahertz steps, but then we can actually, the ADC clock has another divider which we can divide from 2 to the 1 to 2 to the 6, so we can actually get like 0.299 hertz steps in the ADC clock. But the baseband PLL clock rate has bounds that it needs to hit, and the ADC clock rate has bounds that it needs to hit, so it's not always quite this low. But you can kind of see that there are integer steps, even if they're fractional numbers, and no API in the world that I know of actually reports these things as floating point numbers. So this one would get just reported as 2.40000002. And it may just truncate, it may round, it may do floor. It really depends on that API, what the API looks like. And you'll always be half a hertz off, or 0.8 hertz off, or 0.2 hertz off, those kinds of things, which for some algorithms may not be a problem, but for others may be. So the other kind of clock thing is stability, which is, there's kind of 2 aspects to that. One of them was accuracy, which we kind of just talked about. Then there's the drift pieces, like the aging, the drift, the temperature. But then there's also just like movement, like Doppler shift due to mobility. So at 6 gigahertz, at 150 kilometers an hour, you end up with a 0.13 ppm offset just from driving. And this I thought was like, that doesn't happen that much, but this is actually what happens with airplanes. So I'll be giving a talk later this afternoon about ADS-B, and you can actually measure this with ADS-B. Because the airplanes coming at you do travel 400 or 500 kilometers an hour, and the frequency that they're transmitting at is 1 gigahertz. So no matter what you are doing, the algorithm always needs to be able to handle this half ppm offset. And the accuracy in terms of magnitude, a lot of us in the SDR community get the question of like, okay, well, I've got exactly 1 dBm coming out of my source over here. I run it through here. I send it to my PC. I get some numbers. How do I relate those numbers? And the answer is kind of like, sounds great. Because there's relating those numbers, getting that accuracy is, software-defined radios are typically not sold as instrumentation. So you can't confuse a NIST certifiable instrument like National Instruments would make with RTL SDR. They're much different. So, and a lot of it has to do just with calibration. So dBm, so a dBm is an absolute number. It's a dB with respect to a milliwatt. A dBFS, that's a made-up number by ADC manufacturers. So we'll take, so this is dB, is a log ratio with respect to a milliwatt. This is a log ratio with respect to full scale of the ADC or the DAC. So we'll just take full scale and say that's 0 dB FS. And anything in between is just less than that. And the more bits you have, the lower you can go. And then there's just a ratio, which is with respect to something. And so what we talk about in our data sheets is like RSSI, received strength signal. And it will be in dB, it will be linear, it will be monotonic, but 1 dBm of increase will not give you 1 dB of RSSI change. There may be a correction factor you have to apply there. And the correction factor is probably different at different LO frequencies. And so factory calibrations are necessary to limit the amount of variation. And so there's calibrations that you can do on all your radios, but you need to calibrate it to something else. So even us in our lab, we will have Plutos that have been calibrated and are actually, from a power input perspective, are as good as some of the instruments we have, but we use those instruments to calibrate the Plutos. And if we were to do that on every single one, then the prices would be so high nobody would want to buy it. And then, so all of these things can be done. It just takes time, and you have to calibrate them to something else. So whether it's TX power or TX power versus frequency, or LNA step gain, or RSSI on the transmit or the receive side, or even the accuracy of the clock, all of these things can be calibrated, can be corrected, but typically just nobody wants to pay for it unless you are buying something from a National Instruments or Roden Swartz or Tektronix or those kinds of things, where you actually have a calibration sticker on it. The other piece is samples to symbols. So if we have these symbols coming at the right time for a single carrier system, if we sample exactly at the right place, we'll get a nice constellation. If we sample at the wrong place, we'll get not a nice constellation. And if we sample at worse places, we get worse constellations. This is why most systems will oversample. This is why they'll have matched filters. This is why the digital comms guys know all the math. But then, so samples per symbol, depending upon the modulation scheme and algorithm you use, could be 8 samples to 1 symbol or 2 samples to 1 symbol to try and correct for this timing, correct for these modulation pieces. And then we have the 1 symbol is how many bits out. It depends on the modulation scheme you're using. And the error correction you're doing. So we have raw bits, including overhead, versus payload bits excluding overhead. And I think that kind of wraps things up. But it's mathematics. So I was talking to a faculty who told me the value that the secret language engineers have to talk to each other is math. And lawyers use Latin. Physicians do the same. They make up things and then just make it a Latin word and nobody changes it. But math is the language that engineers and scientists use. But it only works when we're all clear, like when we use units, when we have significant figures, and use adjectives to describe our work. It's super important. So if you ever had like a lab report passed back to you by a faculty saying, where's the units on your axis, it's the same kinds of things. So thanks very much for listening, and hopefully that it helps remind people these kinds of things are important so that other people can build on the work that you're doing as you communicate outwards. All right. Thanks.